Okay, so here we go. I am going to do an experiment today where I push the laptop a little forward so I can rest my elbow on the table, and then I think I can use my right hand. I think this is going to be an experiment. I might have to take a 60-second pause in the middle of the lecture to put my sling back on. We'll see. Okay, so here's where we were last time. We were talking about this idea called intermediate variables, which I hadn't really quite gotten to yet, but we started off in that direction. So reminder, we've got a function f that turns the x variables into the y variables. So the x's are the inputs, the y's are the outputs. And here's its Jacobian matrix, derivative matrix right there, right? And then we're going to imagine that it is going to be composed with a function that turns the y variables into the z variables. And let's see, its derivative matrix is right here. The composition then, of course, turns the x's into the z's, and its overall sort of composition derivative matrix is that right there. Okay, so that's the matrix form of the chain rule that we talked about last time. I think should be your sort of cornerstone, sort of, this is ultimately deep down what the chain rule really is. That said, in practice, very often you actually only need to know one specific particular partial derivative. Now, if that's the case, you only need to know just the one specific one. It's an element of a matrix. Specifically, it's an element of a matrix that is itself a product. And you can see exactly how that product goes. It's a dot product where you're going to take these entries here and dot them with these entries here, right? And you can write down how that dot product works. And let's see here. Here's the green entries, and then here's the blue entries, right? And that dot product of the green row with the blue column, right, is this expression right here. And so there is a single sort of standalone formula for how to compute one of the composition partials, right? No matrices required. You can know just this formula right here. And yeah, a whole bunch of stuff you don't have to deal with, right? Notice if you were going to actually multiply the matrices, well, you'd have to compute a bunch of partials up there and a bunch of stuff down here and a bunch of stuff there and there. And then you'd have to multiply the whole, there's a bunch of stuff all over here that you'd have to do that would just take loads of time. Does that make sense to everybody? Okay. So very handy little formula to know. I encourage you to know this formula. Let me do it like that. Good one to know. A couple of things to point out about this. One thing, you got to watch out for a kind of there's a little white lie that they tell you in some single variable calculus classes about canceling differentials. And I want to point out how wildly nonsensical that is in this case. For one thing, and this isn't the reason you can't do it, but this is evidence that you'd better not be able to do it. Look what would happen if I could cancel these. If I could cancel these partial y1s, right? Then notice this is there and this is there, and it would seem that our formula would stop right there, and you wouldn't need any of these extra terms, right? Which we just got through seeing we definitely need, right? So this idea that you can cancel these partial y's gets the wrong answer, so we know it's wrong, right? Now, again, that's not why you can't do it. That's the evidence that you can't do it. The reason you can't do it, the reason this is invalid reasoning is that, well, when you cancel, you're supposed to be canceling the same things. And at a glance, it looks like these are the same thing. But they're not. It's a shortcoming of the notation. It's unfortunate. Notation for this kind of stuff is admittedly a hard problem to come up with good notation that is both fully communicative of what you're talking about and also convenient and practical, right? So anyway, it is what it is, but let me try to explain why those are not the same thing. It's kind of like those are two characters of the same name but in different stories, right? And so if there's a Steve in one, novel, and then in a completely different novel by a completely different author, there's another character named Steve, yeah, they're unrelated, right? They're completely different, right? So that's what's going on here. Let's think about what does this mean right here? What is the partial y1? This partial y1 says how much does y1 change in a certain scenario. The scenario is that the xj variable is going to be changing because we're taking a partial with respect to xj, but all the other x variables are held constant. And now if we think about what happens there, let me come down to this diagram, which, by the way, is going to relate to stuff that we'll talk about in a minute, and I don't want to distract you for the moment. Let's look just at this little diagram here. So xj is changing, and I want to know how much y1 changes as a result, with the understanding that all of these other x variables are being held constant. So that's what the partial y1, this is the story that we're involved in when we look at that first partial y1. Now, here's another observation that I'll make. Now, in this story, if you think about what's happening here, in this story, as xj changes, well, all these other y variables are going to change too. I mean, for the purposes of the partial derivative I'm talking about, I don't actually care how the other y's are changing, but they are, right? So in this story, all of these are changing. How am I going to represent that? I'm just going to kind of circle. All those other y variables are changing. Okay. That's what's happening in the first, the right factor here. Now let's think about what does this mean. That partial y1, part of a totally different story. We're taking a partial with respect to y1 there. And let's think about what that looks like on this diagram. When you're taking a partial with respect to y1, yeah, you're talking about how much y1 changes, but in a scenario where it's required that these all be constant. Well, yeah, but when we're talking about the other partial y1, it's required that they not be held constant. So, totally different scenarios, right? Does that make sense to everybody? They're just unrelated. I mean, the idea that we would treat these two things as being the same and canceling them is just nonsense. You know, the variable x in question number 7 on the homework and the variable x in question number 42 on the homework, yeah, no relation, right? They're just not the same. I hope that makes sense. Is that reasonable? Okay. All right. So it's a nasty little landmine a lot of students step on and get confused. You'd be surprised how often I see students write down this and forget about all of that and just proceed with their calculation that makes no sense, and it's wildly misguided. Okay. All right, so moving along. Okay, so let's try to make sense out of this equation now for copy purposes, convenience of reference purposes. I have recopied it right here, so we're going to try to make sense out of this equation now. What does that look like with respect to the diagram, and how might we make it make sense from the point of view of the diagram? So here's the idea. We're going to assume that xj is changing by some amount. There's xj. It's a partial with respect to xj, so again, all of these other x variables we're going to assume are being held constant. And in this scenario, we want to know how much zi is going to change, and there's zi. Okay, so the big idea is we want to look at all the sort of different, what I'm going to call paths along which these changes in xj can propagate over sort of through the y variables to cause changes in zi. So now here's the first path we'll talk about. Let's talk about as xj changes, that's going to cause a change in y1. And what is the factor? By what factor is it that changes in xj will be multiplied to conclude the corresponding changes in y1? Well, that's the partial derivative. That's one of the things derivatives do, is they relate how much this input changes to correspondingly how much does the output change. So that step in that first path corresponds to that factor right there. Okay, now sure, great, xj changes causes y1 to change, but furthermore, y1 changing, and I emphasize the mere fact of y1 changing. Let's not worry about the fact that y2 and y3, yeah, they're changing too, we'll deal with them in a minute, but merely alone, the fact that y1 is changing will cause some amount of changes in zi. And how much, what is the factor by which the change gets amplified along that section of this first path? Well, that's this partial derivative right there. So how about that, right? Each term, well, we've only looked at the first term here so far, but this first term in our formula from the previous page corresponds perfectly to the idea of keeping track of how changes propagate as you move along this first path. And I argue that by analogy, it's very similar arguments in the same way that this path corresponds to that term. I'm going to say likewise for various other terms all the way down to and including this last path that corresponds to that term. And again, you can look at this last path down here and see, all right, well, xj is going to cause changes in ym. There's that factor. And then whatever those changes in ym are, and considering those alone, ignoring the fact that, blah, 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 other factors, other terms, there's going to be other terms in the expression, but merely the changes in ym will cause changes in zi, and there's that factor. Does that make sense to everybody? All right, so I think this is a really nice way to think about it, and you streamline this, of course, in practice. And in practice, actually I should have left this there. When you're looking at the partial of zi with respect to xj, you can keep track of the various paths. Notice that each path gives rise to a term in your chain rule. Notice further that each path is associated to a single, what we might call intermediate variable, right? It's not one of the input variables. It's not one of the eventual output variables. Intermediate because it's one of the ones in the middle. It's one of the ones that the changes have to pass through. So in practice then, I tend to look at the paths themselves, but you can also kind of think of this as being the y1 term in the chain rule as applied to that partial derivative. And that is just, convenient terminology, convenient little shorthand. Okay, so this in practice is a very convenient way to write down a formula for a partial derivative without having to write down the entire chain rule. And here is an example. So suppose you are given this question right here. So let's see, we have a function that takes x's in and gives y's out, and then composing it with a function that takes y's in and lets z's out. And we want to compute, you'll notice, a specific partial derivative. Now, if we're going to apply these ideas up here, notice that these ideas lean heavily, right, on having this diagram showing how the variables connect to each other. I'm a big believer in those diagrams. I strongly encourage that you use those diagrams as well. So here we go. Let's assemble this diagram. And let's see here. We've got this function that turns the x's into the y's. There it is. Then we've got this function here that turns the y's into the z's. That's that right there. Everybody see how I assembled my diagram so far? Okay. Now, having done that, let me point out we're interested in the partial derivative of z2, which is there, with respect to x2, which is there. And now we're ready to start playing intermediate variables games. So looking at this diagram, what are all of the paths from x2 to z2? What are all of the paths that changes in x2 can propagate along in order to get to z2? And well, there's two paths. I can just draw the pictures right here. So there's the what you might call the y1 path that makes this turn. And then there's the y2 path. Whoa, color coding. The y2 path that makes that turn. Everybody good? No matrix. That I wrote down anyway. There's a matrix. There's matrices underneath all of this, right? But this is the streamlining that allows me to save myself the trouble of writing down a bunch of matrices, most of which I wouldn't even need. Okay. Yeah.
Wait, sorry. Can you show how you know like the x2 arrow points to the y1 and the y2?
How the what now?
The x2 points to the y1 and the y2.
Oh yeah, because x2 is one of the input variables for y1 and y2, right? So you see, we have here. I'll do it like this. y1 and y2 are functions of x1, x2, and x3 by those formulas right there.
Oh, and technically like the x1 and the x3 would also point to each of those, but we don't care about that?
Correct. Yeah, because they're momentarily constant, right? If we're interested in the partial with respect to x2, then x1 and x3 are literally to be treated as constants. Yeah. How are we doing? Is everybody happy? Yeah. Mm-hmm.
Yeah, in this case, do x3 and z3 just doesn't matter at all?
X3 doesn't matter. X3 is constant, right? Because we're doing a partial with respect to x2, so x3 is constant, x1 is constant. And Z3 is just uninvolved in the question at hand, right? Now, somebody pointed out that, so there are other little arrows in here that I just didn't bother drawing because they don't have anything to do with what we're doing. In this question, we're interested only in, let me clean up my mess here. In this question, we are interested only in that partial derivative, and thus I'm focusing only on the part of the diagram that is relevant to that partial derivative. Okay, and then there's little details to be followed. Now, y'all already know how to do all of this stuff, so I'm going to leave most of this to y'all. Let's, real quick, though, how do we make sense out of partial of y1 with respect to x2? All right, well, there's y1. I should do this. I should color code better. There's y1. Take its partial with respect to x2. You get -1. Yeah? Okay. All right. Okay, now, there is a landmine to be worried about here. It's confusion of variables. I like to start with a single variable analog because I love the analogies between single variable and multivariable. And here is a single variable calculus question that I'm not going to spend a lot of time on because this is, y'all know single variable calculus, right? But here's two functions. The question says to compose them and take a derivative. how would we do that? Well, we would use a chain rule, and the chain rule says that the derivative of a product is a product of the individual derivatives, and then we compute these individually. And let's see here, G prime is that, and F prime is that, and then you multiply and you get the wrong answer. Right? Because I was a little too fast and loose with how I applied the chain rule. It is a product of derivatives, but you have to be extra careful that the outside function's derivative is evaluated at the inside function's value. Right? This is the little annoying little fact of sort of the Newton notation for the chain rule. So putting this all together, then let's talk about the G prime. What is G prime? Well, G prime, the derivative of the cubing function is 3 times the squaring function. Right? G is x cubed. Well, to be more precise, G is the function that cubes things, whatever is in there. The derivative of cubing things is 3 times squaring things, but evaluated, and it says so right here, evaluated at f of x, which is x squared. And so it shouldn't be just 3x squared. It's 3 times x squared squared. That fixes the mistake in the wrong solution above. Does that make sense? But it's confusing, isn't it? Right? I find this confusing and annoying. And the much better way around this to me is to just don't confuse your variables in the first place. I think this writing of the question is ridiculous. You want me to compose functions, but you're writing them both in terms of the same variable? It doesn't make any sense. If you're composing functions, right, whatever it is that comes out of the first function, if you're composing them, that had better be the thing that goes in to the second function. Right? That's what composition is. So, much better than what we had above would be to say, all right, well, they gave me the squaring function. The squaring function, the input I'll call x, the output I'll call y. Why not? And then having done that, let's see, G is the cubing function. How am I going to represent the cubing function? Well, again, what came out of F should be what goes in to G. That says my function G should be written where y is the input variable. So, cool, there it is. G in terms of y. Same function, nothing happened to G. Y is just a dummy variable. It's just a placeholder. G of x is x cubed, G of y is y cubed, G of bicycle is bicycle cubed, right? I mean, it's whatever the thing that goes in, cube it. Write it in terms of whatever variable you like, right? So with that understanding that we have rewritten G in terms of y now I can be as careless as I want when I write down the chain rule. It's derivative of compositions, the product of the derivatives. Let's see here. G prime, 3y squared, nothing to it. F prime, 2x, nothing to it. And then you can write that all down. Notice that you get 6y squared x, and then you think to yourself, oh, wait a minute. My composition is entirely a function of x. I need my answer then to be a function of x. And so I'd better get rid of the y. How am I going to get rid of the y? Well, we get rid of the y by recognizing that what y was. The input to the G function, right, was chosen as such because it is the output from the F function. And so this little formula here for y goes in there, and then you get what we all knew was going to be the right answer anyway, 6x to the 5th. Is that cool? All right, so it's tedious little consideration of stuff you already knew, single variable calculus. Don't confuse your variables. Right? It's a nice little simple lesson. Okay, now let's just use that same idea then in a multivariable setting. By the way, questions will come at you written like this. Perfectly good function of two variables. Here's another perfectly good function of two variables. No problem. You can write you can write two different functions in terms of the same variables. There's no law against that. Now, when the question further goes on and says, hey, I want to compose those functions, this is the point where you should think, oh, hey, whoa, dude, you want to compose these functions, but they're written in terms of the same variable. We have a confusion of variables problem. At that point, that's when you need to rewrite one of your functions. Now, what I tend to do is to go ahead and whichever function acts first. And let's see here, we have this function f that acts first, you'll notice, because it's on the right in the composition. I remind you, be really careful about the orders. It's unfortunate that notation has done this to us, but the function that's on the right in the composition is actually the one that acts first, and therefore is on the left in the diagram. Yeah, it's annoying, but that's where we are in this world. So heads up. F, let's see here. I'm going to leave written in terms of x and y because I have no reason not to. The outputs, what I'm going to call the outputs, can't call them x and y. Those are the inputs. So the outputs I have to call something else. And again, whatever you call these outputs from F are also going to be your inputs to G, and that's your tip-off that you need to write. You need to rewrite the function G in terms of U and V. And I emphasize here, I didn't do anything to the function. It's the same function G. I'm just writing it in terms of different dummy variables. Choose whatever variables you like. Who cares? Right? But now that we've rewritten it, right, and just to avoid potential confusion, I'm going to scratch off this original, right, all of this. Well, of course, the left part's fine, but just to be consistent, we're not going with the original phrasing anymore. We're going with our new phrasing here, and this is our diagram keeping track of what's a function of what. And now you can write down the chain rule, and everything works just fine. Certain details you have to keep track of. Compute the corresponding derivative matrices. You multiply to get the derivative of the composition. Make sure you put the right one on the right side. You got to be careful with that. And then just remember at the end, right? G is a function of U and V. U, of course, is the output with the first output from the f function. So everywhere I see a U, whoops, I missed, sorry. Everywhere you see a U, you've got to put whatever the function f says it is. So x squared plus y squared. Everybody happy? Likewise for the v, and then you multiply the matrices, whatever. Okay, dangerous little landmine. Okay, here's a related worry. We entered this discussion talking about composing multivariable vector-valued functions. Right? So we have one function with several inputs, several outputs, then a second function with several inputs, several outputs, and composing them. When you compose functions, there are certain things that are just, the part of what it means to compose functions. In order for these things to even be functions, if I want to say f is a function, well, implicitly, these inputs are independent. They have to be independent variables, right? That's part of the deal. Secondly, let's see here. The outputs from the first function have to be the same as the inputs into the next function. Again, that's what it means to compose two functions. Is that what comes out of one, you put it into the next. Okay, so whenever you have a composition of two functions, you get a corresponding diagram. It does not follow that every diagram represents a composition of functions, right? So here is, over on the right here, we have a representation of a diagram that represents certain relationships between certain variables. And, for example, you look at this algebra down here. Here's a bunch of equations relating certain variables, and notice this is where the diagram came from, kind of, that y1 is x1 plus x2. y1 is a function of x1 and x2, et cetera, right on down the line. Now, I ask, though, that being said, looking at this diagram, does that represent a composition of functions in this sense over here? And no, it really doesn't. I don't know what that is. That's not, as written, that is not a composition of two multivariable vector valued functions. It's just not. Right? So, for example, it's tempting to say that, maybe Z1 is a function of, it kind of comes at us as being a function of x1, y1, and y2. I mean, you see that in the formula right here, right? But let's see here. Are those independent as they should be? No, they're not. y1 is a function of x1. Right, so that's I don't know what that is. I don't know what's going on. Okay, I think the way to deal with this is to fix the problem instead of trying to limp along with the problem. So it turns out this is actually pretty easy to fix. And that is, we're just going to enter. Actually, I need the whole thing on the screen. Let me zoom out and we can fit it all. Yeah, here we go. We can fix the diagram basically by just introducing a new variable, kind of, if you will, there in the diagram. And if you introduce a new variable there, we're going to call it x1 star, just like I did here. Notice the diagram that is, I don't know what this is, right? This sad story over here turns into a perfectly decent diagram here. Right? This is a composition of two vector value multivariable functions, right? I've got my input variables, then I've got my intermediate variables, then I've got my eventual output variables, and the outputs from the first is the inputs to the second, and it's fine. Perfectly recognizable. Now we are actually dealing with a composition of two functions, and we can talk about the chain rule, because that's what our chain rule does. Our chain rule addresses this scenario, not that. I don't know what that is. Does that make sense to everybody? So, okay, cool. Now, things look a little different when you do this. Let's look, for example, at this Z1 business like we were before. Z1, previously, I was like, that's weird. Z1 is a function of those. Wait, is it? Oh, but those aren't independent. What's going on? Now, Z1 doesn't depend in part on x1. It depends on x1 star, which is x1, right? But we're calling it x1 star. We're treating it as a different variable, however simple its formula is, right? And so I have to rewrite the formula for Z1 correspondingly, right? It's not x1 plus y1 plus y2. It's x1 star plus y1 plus y2. and now we're in business. All right, so forget about all this confusion up here, whatever's going on there. I've got a new diagram. I've got a new collection of equations. Right, we've jettisoned that, and now we're in business. Let's see here. Let me zoom out, and we can start talking about the chain rule. And if somebody asks, for example, what is the partial of z1 with respect to x1? All right, well, let me clean up my mess here. Z1 is there. We want the partial with respect to x1, which is there. No sweat. I have 3 paths through 3 intermediate variables, thus giving me 3 terms, and proceed. Everything's fine. Everybody see what happened there? Yeah.
But if we're equating x1 stored to x1.
I'm sorry, say again?
If we're equating x1 stored to x1.
Yeah.
Then what does this accomplish?
What is the what?
If x1 stored equals x1.
Yes.
What does this accomplish?
This accomplishes allowing me to actually view this as being a composition of 2 actual functions, which is the premise of the chain rule. Right? The chain rule that we wrote down is about composing 2 actual functions, and this up here is not that. You know what I mean? It's not. This is a tangled web of relationships. Right? Every composition of functions creates a diagram, but there's plenty of diagrams that don't come from a composition of functions. So here's another way to say it. I mean, let's ask the question here, as I have written down in this diagram. What does the partial of z1 with respect to x1 mean? Okay, well, let's see here. Here's z1. That's there. Z1 is a function of these variables. I want to take the partial with respect to x1. That means this is a variable, but now y1's got to be a constant and y2 has got to be a constant. But you can't, because look at this. The formula for y1 depends on x1. If x1 is changing, y1 will be changing too. I can't hold it constant. This is confused garbage nonsense. Does that make sense? So you have to. It violates these rules. It isn't this nice simple story right here. So you just can't do business with this. This is not a shorthand for a composition of functions. And so I don't know what it is, but we can't apply our chain rule to it. All right. Okay, so nice little trick. By the way, this scenario comes up fairly often. I would say that you have a bunch of equations given to you, right? And then they say compute the partial of blah with respect to blah, and you take those equations, and the very first thing you're going to write down when you see that list of equations is you're going to find yourself looking at a diagram kind of like this. And then you're going to realize I can't apply the chain rule to that. That's not a composition of functions. And so then you pull this little move and introduce a new variable as needed to fix it, and then go about your business. Okay. All right. Okay. Let's talk about second derivatives. It's actually pretty straightforward. It's just you have to go slowly and carefully. It's a very delicate business, but ultimately it's just exactly what it ought to be. So I'm not going to state any theorems on this. I'm just going to kind of show you kind of a working example. By the way, this example I'm about to start off with is the classic first example that everybody uses. Here we go. So suppose we have z as a function of x and y. By the way, I'm going to assume it's a nice function. So in particular, it's C2, so that's twice continuously differentiable, which I need in order to be able to do the stuff that I'm about to do. Okay. All right. Okay. Then r and theta are polar coordinates, and y'all remember polar coordinates, and in particular, when you have polar coordinates, x and y are functions of r and theta. So let's make ourselves a diagram here. Z being a function of x and y, cool. There's that part of the diagram. X and y being functions of r and theta, fine. There's that part of the diagram. So I've built up my diagram. Is everybody on board? Okay. You'll notice the question asks for the second partial of z with respect to r. Let's slow down. Let's first things first. Let's try to find the partial of z with respect to r. And reminder, here's z, here's r. Whoops. Two paths, two terms. Yeah, that's just our intermediate variables point of view on the chain rule. And then notice a couple of lucky breaks. By the way, for the moment, let me cross out this. I don't want to. We'll get to this in a few minutes, but for the moment, don't look at that. Looking at our original diagram, let's ask what is the partial of x with respect to r. Reminder: x is there, r is there. We're taking a partial with respect to that r. That means that theta is a constant, right? Notice how I'm going very slowly here, right? I'm thinking carefully as I look at each one of these factors. What's the variable? What's the output variable? What's the input variable? What does that mean about which variables are constant? So I get to treat theta as a constant, and if I take the classic formula for x, r cosine theta, treat that theta as a constant. Therefore, cosine theta is a constant. Take the derivative with respect to just r. I get, just cosine theta as the result. Is that cool? Okay, similarly there. And then notice all I did otherwise here is rewrite sort of the notation, right? Partial of z with respect to x. Okay, I like this subscript notation instead. It's just a little easier right now. Okay. All right. So that was our first partial. Now keep in mind what we wanted was the second partial, which means I'm going to need to take my first partial with respect to r and take its partial with respect to r. Right? And reminder, when you're taking a partial with respect to r, I'm taking a partial with respect to r, that means that theta is a constant. Right? Always have your diagram, right, conveniently available to look at and remind yourself, wait a minute, which variables are doing what at what point in the calculation. So I'm taking a partial with respect to r. That means theta is a constant. And if theta is a constant, then that also means that cosine theta also a constant. Sine theta also a constant. And a convenient fact about constant factors, of course, is that they factor right out of a derivative. How are we doing so far? Everybody with me? Okay. Slowly and carefully. Okay. All right. Now here's where we have to fix our diagram. Let's look at this expression right here that we've ended up with. Partial of zx with respect to r. What are we going to do about that? Let me show you the wrong move. Let me show you what a lot of students write down that's completely wrong. Right? It makes no sense at all, but it's super tempting. So this is a dangerous landmine. Right? Some students will look at this and say, oh, okay, well, I'm going to view this as the second partial of z with respect to r with respect to x. So x partial first and then r partial second, apparently. Right? Now, some students will write this down happily. And I claim that doesn't make any sense. Because this suggests, right, this right here suggests that z is a function of a collection of variables that includes both r and x. This is not a function. Right? I can't talk about z being a function of r and theta and x and y. These aren't independent of each other. Directly and blatantly, right? The r and the x is itself a function of r. So I can't just say, oh, I'm going to hold one of these input variables constant. I'm going to hold 3 of those 4 input variables constant, but I'm going to let r be a variable. You can't. That's not if r is a variable, then x and y can't be constants, right? So that just doesn't make any sense. Is everybody on board? And I know it's tempting and it's frustrating that things that look like they ought to kind of work from a symbolic point of view are, dangerous garbage, right? But that's the reality here. And so your way out of this is to diligently rely on and obey what your diagram says, right? And follow the rules carefully. Right? You can't take a symbolic manipulation only point of view on this. You're going to accidentally write down garbage, and then everything. It's all, catastrophic, car fire after that. Okay. All right. So how do we treat this? What is the better way to deal with this thing? And the answer is to recognize what zx is and include that on the diagram. If I want to take a partial of zx, what is zx? Okay, well, z was a function of x and y. I'm just kind of thinking out loud here. If z was a function of x and y, and you imagine some expression involving x's and y's, what happens when you take a partial with respect to x? You get some other function of x and y. So zx is literally a function of x and y, and I recognize it as such on our modified appended diagram. And then when I talk about taking a partial with respect to r, as it says right there, well, r is over here. And altogether then I have, let's see here, I want the partial of that blue with respect to that orange, and then no problem. Chain rule is going to totally do that for us. And in particular, there's that red path, which gives you this red term in the chain rule. And then there is this purple. Oh, that's pretty bad. Let me do that again. Purple path, which gives you that purple term. And altogether, that's hard. Altogether, then, this is how you rewrite this thing right here. Right? This second derivative of sorts. Chain rule, using our appropriately modified diagram representing what are we actually dealing with, what's a function of what. And again, just following the rules. Does that make sense to everybody? Careful. Slowly and carefully. Right? There is a temptation to try to leapfrog and go straight from here down to there, all in one step or something, like you're saving paper or you're saving ink or pencil lead or pixels, right? Which are free, right? But don't worry about that. Don't try to save pencil lead, right? Pencils are cheap, right? take each step slowly and carefully, and it'll keep you on track. Okay, yeah.
What happens to Z in all of this? Does it just not matter when you get to the second difference?
I mean, it's there. We'll deal with it if it comes up again. It won't. But yeah, it's sort of done its job. Yeah, so it's not going to be in the resulting calculation yet. Okay, so y'all can think through for yourselves. Everything else is kind of all downhill from here. So this gives that by the same argument, and then it's just kind of notation from here on down. Okay, see y'all later. Have a good rest of your Monday. Like that.